Hello everybody. In this video we're going to be covering section 14.7, acid-base titration. We're going to learn how to interpret acid-base curves for strong and weak acid-base systems. We're going to compute sample pH at normal stages of a titration, and we're going to explain the function of acid-base indicators. So a titration curve is a plot of some solution property versus the amount of added titrant. So we're going to measure some property that allows us to measure the concentration indirectly of a system as we add a titrant. In the case of acids and bases, that thing that we're going to measure is typically going to be pH, because it's going to allow us to predict the solution composition. The shape of the titration curve is affected by the strength of the titrand or analyte, the thing that we're going to titrate, our unknown sample, and the titrant, the stuff that we know the concentration of that we're going to be adding to it. There's a few stages of a titration plot. The initial state, where we've added 0 milliliters, the pH is going to be determined by the acid being titrated. So now we're just talking about the pH of the acid that we have started off with, our analyte. When concentrations are held equal, stronger acids are going to have a lower pH. Pre-equivalence point, the solution pH is going to increase gradually, and the acid is consumed by reaction with the added titrant. This is also called the buffering region, because what we're doing is we're setting up a buffer where we have the initial acid still there, but we're also producing as we go along some of the conjugate base of that solution, of that acid. Finally, we're going to have the equivalence points. This is where we're going to see a drastic rise in pH. All right, the solution composition transitions from being from acidic to either neutral or basic. All right. So the pH is determined by ionization constant of conjugate base of the acid. Post-equivalence point, pH is determined by the amount of excess strong base titrant added. So here we can see some of the general shapes for a strong and a weak acid being titrated. I am going to note that everything that we just covered starts with the assumption that I had an unknown acid and added base in order to produce these curves. But it could have easily been the other way. I could have had an unknown base and added acid, at which case this point would have been up here, and then it just would have followed the same sort of pattern going the other way. Okay, so here we start off at the very beginning point where we have a 1 based on the fact that we had 0.1 molar, based on the fact of the acid that we started with. Okay, we start adding a volume of 0.1 molar sodium hydroxide. We're into this buffering region here, our pre-equivalence point. All of a sudden, its pH is going to change drastically. Okay, and then we're going to enter into a new buffering region up here. For a weak acid, we're going to have a higher starting point. We're going to have a sometimes more complicated looking buffering point here. The entire thing is a little bit less sharp. It's a little bit more squashed down, and this equivalence point is a little less obvious than it would be, but it's there. And then we enter into a new buffering region. The equivalence point right here at the center of this sharp rise is actually a true inflection point for those of you that are actually interested in calculus. This is a point where the second derivative of this function changes sign. And it can actually be found using numerical derivative techniques. One other feature I wanted to point out here is that when we had a strong acid and a strong base, our equivalence point was right around neutral, whereas when we added a strong base and we had a weak acid, the equivalence point was at a basic point. Okay, If we had a different system where we had a weak base and a strong acid, its equivalence point would have been down into the acidic region. So let's talk a little bit about acid-base indicators. As we've alluded to several times now, certain organic substances change color in dilute solution when the hydronium ion concentration reaches a particular value, so we can add dyes that are going to change color based on pH. These substances are called acid-base indicators and can be used to determine the pH of a solution. We can talk a little bit about how that works out mathematically here. The equilibrium in a solution of an acid-base indicator, say methyl orange, can be represented by an equation in which we use HIN, so hydrogen bound to the indicator, as a simple representation. So here I have the acidic version of the indicator. I add it to water, it produces hydronium, and then the conjugate base of the indicator. So when it's protonated, it is red. When it's deprotonated, it is yellow. Okay. If I added acid to the system, I'm going to shift the equilibrium over to here, and we're going to have a red solution. If I add base, I'm going to shift the equilibrium over to here, and it's going to turn yellow. If we look at this mathematically, we can have the Ka of this reaction here. It's going to be equal to 4 times 10 to the negative 4. I can plug that into the Henderson-Hasselbalch equation here, and what I will see is that when these solutions pH is above 4, so more basic than 4, that means that this guy here is dominating, so I have more of this than I do this, and I get that yellow solution. And when it is below 4, I'm going to have the protonated version dominating, meaning I'm going to have a red solution. There is a color change interval for acid-base indicators, and this can be a fairly wide range. And what this means is that direction matters, okay? We're going to see color changes for all of these indicators in this region, and it's going to depend on whether I come from a low pH to a higher pH or from a higher pH to a lower pH. When I'm going to first see that color change, okay? So you have to consider that whenever you're choosing your indicator, all right? You have to consider whether or not which direction you're coming from when you're first going to be able to detect a color change. An appropriate indicator should have a color change interval that encompasses the equivalence point. Okay, so if I'm looking here where if I plotted this out, I'd have an equivalence point right here. The only choice that I would have out of these three would be the litmus. Whereas if I had one like this, where my equivalence point was right here, I would want to choose something like phenolphthalein. Methyl orange would not be a reasonable choice for either of these two titration curves.